All right, let's walk through this problem. A hollow sphere rolling along a horizontal floor at 6.5 meters per second when it comes to a 40-degree incline. How far up the incline does it roll before reversing direction? So the sphere has been rolling. It reaches a 40-degree incline. This 6.5 meters per second is, since it's a meters per second, it's V, so that's going to be V of the center of mass. That's the speed it has as it approaches the incline, and then it's going to continue rolling until it reaches a maximum height, which is where, of course, it will reverse direction and come back. So at this maximum height, the speed of the center of mass will be 0. It will stop for a split second. It's turning around, and it's going to roll back down the hill. All right, so conservation of energy. We can totally say that the initial kinetic energy this sphere has turns into gravitational potential energy. But with the sphere is rolling, this initial kinetic energy is both translational, so 1/2 mv squared, because it's rolling along a surface, but it is also rotational, because it's rolling as well. It's rotating around its center of mass. So we do need to account for both types of kinetic energy. All of this kinetic energy is going to turn into mgy, the gravitational potential energy. And again, we need to look at the vertical height the center of mass specifically moves through. If I draw my sphere over at the bottom, I know the center of mass of the sphere is in its geometric center, and I'm looking at the height that the sphere rolls through. So technically I'm measuring center to center. That will ultimately, in this case, be the same as measuring from the bottom of the sphere to the bottom as well. So if that makes better sense to you, we can look at that as well. The center and the bottom of the sphere are a radius apart. Now, ultimately, we're looking for the distance along the incline the sphere has rolled. Since it's asking how far up the incline does it roll, that means this distance d. So we know d and y are related. We can say that the sine of 40 degrees is this vertical y final over the distance it moved through. So we can say that y final is d sine 40. So coming back to our conservation of energy equation, we don't know the mass of the sphere. We do know the speed, and we know the speed of the center of mass is related to the rotation rate through r. So v of the center of mass is r times omega. I is the rotational inertia, or moment of inertia. If we look on the table, either in the test notes or in the book, this sphere is rotating around its axis, around its center of mass. When I look at a hollow shell, so a hollow sphere, the table tells me that I is 2/3 mr squared. So I'm going to make these substitutions. In place of omega, I'm going to put v over r. Since we know v, I'm going to put that in for omega. I'm going to substitute in I, and I'm going to substitute in y is d sine 40. So 1/2 mv squared plus 1/2 2/3 mr squared for I, and then omega when we do this, the mass is in every term, so the mass cancels, which is nice. The mass doesn't matter. So we have 1/2 v center of mass squared. Here the 2's cancel, so I have 1/3. But the r's here, I have r squared in the I, and this substitution for omega has to be squared, so the r's squareds are going to cancel. I end up with just 1/3 v center of mass squared equal to g d sine 40. So the mass doesn't matter, the radius doesn't matter. As long as the object is rolling without slipping here, the mass and the radius both cancel when we write the energy in terms of the speed of the speed of the center of mass, so meters per second. So let's see, let's get a common denominator here. So 6, that would be 3, 2. So 5/6 v center of mass squared. We know the speed of the center of mass. They gave that to us. That's what the 6.5 is. We know g. We're looking for d. So if I solve for d, the distance up the incline, this is how far along the incline the sphere will roll. I'm getting 5.59 meters. Looking back to the question, there's 3 sig figs in both of those numbers. Yeah, technically 9.8 is rounded to 2 sig figs, so I guess 5.6 is good as well. So that's how far along the incline this sphere will roll. Now, just a side note here, if this was a solid sphere, I would have been 2/5 mr squared. Ultimately, the difference would be this coefficient in front of the mr squared. Coming back to our equation, a solid sphere, it has an I of 2/5 mr squared. The 2/5 is smaller than the 2/3 for this hollow sphere. This number would be smaller, which means the whole left side would be smaller, the whole left side of the equation, which means D, if this left side over here ends up being smaller, that means D will end up being smaller. The smaller the moment of inertia, the smaller the I value, the less distance, the smaller the distance, the object will travel up the incline. Another way to think of that is just moment of inertia is a resistance to a change in rotation. A smaller I does not resist that change as much, and so it slows down faster. The hollow sphere goes farther, because it has a larger I value. And so everything in terms of this motion boils down to that coefficient. So even if we were to plug in 2/5 mr squared, the masses would cancel, the radii will cancel. And so we would end up with just that coefficient in there. That coefficient, the smaller the value, the smaller the I value overall, the less distance it travels up the incline because it's easier to change its rotation.